It's really a pleasure and an honor to be here. I would say that Daphne's a tough act to follow, except I've actually sort of been following her my entire career. So when I was a neuroscience PhD student right over here in the medical school, Daphne was teaching computer science just across Campus Drive. And in about 2001, I took a class from her that was an introduction to artificial intelligence. And that's how I ended up in this field, is by seeing the possibility for how that work could impact the trajectory of science overall. And the talk that I'm going to give you is really taking us and putting things into perspective. And it's going to be much less about the details of the scientific discoveries that we've made. We're going to be talking about that a lot today. But in some sense, I want us to think about where is this all going and what is the trajectory of the revolution that we find ourselves in. And I'm going to rely largely on medical imaging as an example, but I'll make allusions to how this has impacted other fields like genomics. So I think one of the things that has changed radically since I was a graduate student and Daphne was a professor, is that we've taught machines to be able to see what we see. And at this point, I believe that if humans can reliably see something in an image, with time and patience, a machine can be taught to see those same phenomena. And this is groundbreaking. This is transformative. This is what's giving rise to everything from synthetic image creation to self-driving cars to the kinds of revolutions in medical imaging that we're talking about here in the radiology department. And the way that we did this was really by combining three techniques. We took deep neural architectures, which were things that had been in people's minds since the 1950s, the idea that we should use smaller computational units that learn to work together rather than being programmed to work together. That was around for a long time, but it didn't really work until we had the computing power to make it happen. And the other thing that we realized that's been incredibly important, particularly in the field of medical imaging, is the value of transfer learning. And the idea of transfer learning is that we don't just train the system to do the one ultimate objective, but we give it experience about things in a broader domain. And this fundamentally is an incredibly important part of how human beings are able to learn so quickly from so few examples, is that we have knowledge about the world. We have learned to see in general, and we can from there learn to see specific and individual cases. And this is incredibly important in the way that deep learning systems work today in industrial settings and in academic settings. You begin by training your neural network on a general class of images. That might be a supervised task or an unsupervised task, but the system learns to see in general before it learns in particular. And then supervised learning is really about taking the machine and driving it to see exactly what it is that you want to see with a specific labeled data set that you curate carefully so that it sees what's important for your objectives. And this has been wildly successful. And it holds the promise of something that we really want to see in this field, which I'll summarize kind of somewhat crassly as automation. And I think that this is an important thing for us to work on. It's the right thing for the imaging community to attend to at this juncture in history. I don't want to distract us from the idea that this is what we should be doing. We should be teaching the machines to see what we see. It offers a great many benefits, practical benefits to the world. I believe that this will radically increase the accuracy, the aggregate accuracy that we deliver to the population in terms of diagnosis. It increases the reliability of these systems. It increases the consistency with which they treat patients over time and across geographies. But there are other advantages as well. So in the fireside chat later today, we're going to talk about ethics and bias in machine learning systems. This is an incredibly important topic. The reason why it's so important is because our ability to measure bias in machine learning systems is so much better and so much more precise. It's not, in my view, that machine learning systems are more biased than humans. It's that we can quantify it immediately and we can correct it. And I think that the quantification of bias in these systems is an opportunity for us to make systems that are more fair, more equitable, and more available. And of course, automation usually brings lower costs and greater access. That's often why we automate manufacturing processes and things like that. But it's also circumscribed. It's one aspect of what it is that we want to do. We want to teach the machines to see things that we see. But that is kind of a limited framing of the potential of machine learning and the potential of machine learning in medical imaging in particular. And the reason is that machines can actually learn to see things we can't. And that's a really important observation, and it changes the framing of what it is that we're trying to accomplish. And I'd like to spend the next few minutes talking to you about what I mean by that. And the first place that I saw this was actually in screening for diabetic retinopathy. We were working with an underserved population in India, trying to build an automated system to identify which patients should be referred to specialists to control the degeneration of their retina brought about by diabetes. And the system was working well, but we had an intern who was, she was trying to debug part of the training pipeline. And in the debugging process, she thought it would be a good idea to try to teach the machine to learn something it couldn't possibly learn from a retinal image. Let's ask it to predict the sex of the patient. AUC should be 0.5, should be a chance, obviously, right? Well, it wasn't. So we thought we had, well, now we knew we had a really big bug. But it turned out, actually you could. You could see chromosomal sex in retinal images. And that was a surprise. And then we saw other things that it could see. You could regress out age. You could see hemoglobin A1C scores. You could see a surprising array of things in the retina, some more surprising, some less surprising. You could interrogate the image and ask, where in the image did you see this? And often it was the microvasculature. That was a shock to the ophthalmologists and retinal specialists on our own team, and indeed in the larger community, that the machine, from not incredibly high resolution data, was seeing things in the image that the human didn't see. But that was just one example. Another example that some of you are familiar with is that actually just from consumer RGB video, you can measure people's heart rate. And that's because of subtle fluctuations in skin tone that are captured at the regular frame rate that is captured in video. But when you look at a video, you don't see people strobing with their heartbeats, but there's enough of a residual signal there that it's detectable. And you can actually do this now on your Pixel phone. You can put your finger over the camera and measure your heart rate. You can also measure someone's respiratory rate to a higher degree of accuracy than sort of your average intern can, just from the video. So it can see things that humans aren't seeing, but at first you might say, well, maybe this is just finer grained discriminations, right? Those first two examples I gave you, that seems like, well, they picked out something in the image, and if we had better pre-processing and better filtering and we trained people to look for these things, humans could see these things too. I think that's probably true in the cases that I gave, but there are cases that go much further than that. And I think that's really important, and that's where I think the shift happens, is that it's not just doing more and drilling down further into existing images, but it's looking at what images should be if we want them to be the most informative. And one of the things that I think is really important here is the use of higher dimensional data, or data that isn't immediately obvious to humans what it means. So I think that there's burning examples going on in the field of microscopy, like the phase microscope that Daphne showed, or in histopathology with multispectral imaging, where we're able to look at data that to the human just looks like a mishmash. It's too much information to take in at one time. And we may be able to train machines to use those data in constructive ways. And fundamentally, I believe that higher resolution imaging, virtual staining, hallucinated staining, as you say, when you try to bring it back into the image domain so that we understand it, that information is there, and we need to get comfortable with the idea that a machine may be able to extract information from an image that is not immediately obvious to us. I think another thing that this might lead to is less pre-processing. When I was here at Stanford, I did a bunch of MRI work, right? And you're always transforming it back into the image domain. What about actually trying to learn in the Fourier domain? There's extra data there. Maybe there's extra signal there. Maybe it's all noise. But the opportunity to say, let's look at things that are more raw and understand if we're leaving some diagnostic power on the table. And one of the things that I really care about is the promise of using lower quality image sensors, cheaper image sensors, in order to get the job done. And this is one of the reasons why I really like working at Google, where you can get to play with the sensors that are on things like a phone and understand what's the potential. We're taking our work that we're using laser scanning retinal microscopes and seeing, well, what can you do with a photo of the external eye? What can you do for dermatological screening? What can you do with a microphone on a phone in order to hear someone's heart rhythm? These things may be not quite good enough for humans to make the sort of distinctions that we need for medical uses. But if we can push care to the edge and get signals early, the possibility of being able to track the progression of disease and understand its dynamics, I think radically improves. And I think we should be expecting that kind of thing to happen, because I don't really think we're gonna put CT machines everywhere in the world where they would be useful. I think we're gonna find ways of having lower fidelity sensors deeper into the community that help us bring people into those high quality sensing situations when we need to. And I think there's also the machine's ability to work with images in time, movies. And so an example of this is that a lot of companies have been working on lower cost ultrasound sensors, things that are handheld and portable, and that's great. But in a low and middle income country setting, you don't just have the problem of the cost of the sensor, you have the absence of the skilled operator, the sonographer, who's able to position the device and interpret the image. It's an active image acquisition problem. It's not a passive one. Well, how do you solve that with AI? Well, one thing that we did that actually seems to be working is you can just teach someone to take one of these low-cost sensors and sweep it in a blind kind of mowing the lawn pattern, for example, across a mother's belly. And you can take that sequential data, which when you look at it as human, it's just things flashing by in a flood and shadows and bright spots. Take that stack and learn directly on that stack. And you can get gestational age to a higher level of accuracy than a trained sonographer. That's just a proof of principle, but the idea to me that you can look at things as they progress in time and fundamentally see things that you wouldn't normally collect the image that way. And I think this same thing happens when you pull out to a larger dilation of time. So I'm talking about disease progression in particular. So we've done some work, again in ophthalmology, showing that you can do progression prediction directly from images at a higher level of accuracy than I really thought would be possible. And I think that this fundamentally leads us to the idea that what we can do is we can look at these things as a better way of viewing prognosis and as a better way of looking at treatment response forecasting. And again, I'm following Daphne, right? That's exactly what she was talking about. She was talking about seeing more in the data in order to be able to forecast how a system will respond to treatment. But in the last bit, I really want to orient towards, well, what does this mean conceptually? What am I advocating for conceptually? And what I'd really like to you to try to think about is think about the process of a disease as a trajectory in an abstract and dimensional space, in an embedding space. This was also something that Daphne was using. The idea here is that normally when we learn from these medical images, one of the things that we do is we map the high dimensional image into a lower dimensional space, maybe a few hundred dimensions, still too big for us to think about, and we make classifications based on its position. But as that patient evolves, that image undergoes a trajectory. The evolution of their disease, or the natural evolution of their body through aging, that is a trajectory in an n-dimensional embedding space. And if we can, and in some sense, you can take that embedding and you can hallucinate, you can project it back, right? And say, well, what would this look like in a few years? Fundamentally, this is how these cute things where you can take a picture of yourself and then see what you would look like as a kid or see what you'd look like as an old person. That's what they're doing. They're moving your image in embedding space and then projecting it back. We should be thinking about disease that way. And if we think about disease that way, I think this fundamentally changes our framing of artificial intelligence in medicine and in imaging, which is that it's not just about taking the sensors that we have, the tests that we have, the data that we have, and understanding it and making discriminations on it. That is what we should be doing right now. But a decade from now, we better be thinking about, well, how do we actually change what we measure, change what we sense to get the most information out of it, to care for patients best, to have the best forward model of how disease progresses and what interventions we might need, what interventions might cause. I actually believe that it will be possible to say, this is the trajectory of your disease in embedding space without treatment, and this is your predicted trajectory with treatment, or with this other treatment. And that, I think, is, in some sense, the holy grail that we should be aspiring for. Thank you so much. I really appreciate the time and the open mind to crazy ideas.
Good morning again, everyone. And today I'll tell you about the long tail of diseases, the long tail of diseases that start out very mysterious and how we've actually conquered that long tail to the point that really all we need is implementation. This is a story I'll tell you today. So the story today is a story of monogenic diseases. This is a very large subset of rare diseases, and these are the diseases that are caused by mutations to a single gene, okay? They make up the vast majority of rare diseases, and the genomic revolution has allowed us now to diagnose thousands of these diseases. So we can diagnose about 7,000 of these diseases to 4,000 different genes. There are 20,000 genes in our genome, however, and effectively for the last decade, every business day, we've been publishing on a novel disease gene. So about 250 novel monogenic disease genes are published every year for a decade now. So what I'll try to show you today is that we as scientists are at a point where we can diagnose all monogenic diseases. All we need is to incentivize the system to build what we have prototyped, and I'll explain to you what we've prototyped here. Okay, so here's what you need to diagnose absolutely all monogenic patients. First of all, you need the capacity to take new patients that come to the clinic and find a name for their disease. Okay, I told you we have 7,000 of these diseases that we can diagnose right now. Get a patient, match them to the right disease. Get another patient, match them to the disease. Second thing you need to do is you need to accelerate the rate and ultimately exhaust the pool of monogenic diseases. So I'll show you how we can discover and name novel monogenic diseases and tag them to the genes that cause them. And essentially, all you need to do then is repeat cost effectively, right? Diagnose patients with diseases you know, deplete the set of diseases you don't know, repeat this until the set of diseases is depleted and the set of patients all are getting diagnosed and then progress on into treatments, et cetera, et cetera, et cetera. So like I said, we as scientists know how to do 1, 2, and 3. And when you look at it as a scientist and you ask what's missing, I guess it's incentive. So that's the case I'm going to make today. Okay, so actually monogenic disease diagnosis is tough, right? Doctors know that. Why is that tough? Because there are thousands of diseases. Okay, it's a very long tail of exotic diseases. Some of them would have as few as a dozen patients known across the world, maybe even like 2 or 3 of them. Each patient presents with dozens of different phenotypes. Out of thousands of different possible phenotypes, there are thousands of variants in each patient genome, even when you sequence them. So you really need an encyclopedic memory to even start tackling these diseases, or the other way that we tackle them is by expert panels. Different experts specialize in different groups of a few hundreds of these diseases, sit together in a room, try to decide what happens with it. But it turns out that actually computer diagnosis is easy. Okay, a computer is exactly the beast you want that you can instill with encyclopedic memory. And as I'll show you, if you craft the diagnosis as a query, the computer will simply go and do that for you. So let's do that now. Let's go diagnose the way a computer would diagnose. Okay? So here's patient diagnosis for you. First of all, let's define the goal as a query. Find one or two variants in the patient genome that, according to the current literature, our knowledge of medicine, explain the patient's set of phenotypes. That's it. That is your diagnosis. Find the variant that, according to the literature, explains your patient's set of phenotypes. You have a disease in your hand. Okay, notice that I'm going to talk mostly about genomics, but really, you can get those candidate genes from anywhere, from transcriptomics, from enhancer work, from anywhere you want, as long as you can evaluate your candidate, see what you know about a set of phenotypes that it produces when it's perturbed, and see how good of a match that is to your patient. If you iterate over all patient variants, over all known literature, and over all set of phenotypes of the patient, you'll do a really good job, turns out. Okay? So that's essentially what we do. We will get sequencing data or any other omics data and completely automatically process that to the stage where we have a set of candidate variants in the patient, that you never see in healthy individuals. And you can predict their pathogenicity. There's a lot of, I'll unfold all of it, and then I'll go back and reflect on that. All of these are powered by machine learning. I wouldn't put the processes in front of you, but all of these are powered by machine learning. The variant calling, pathogenicity prediction, all of it. Then you take the patient medical record, which gladly for us is all digitized, and you extract the patient's set of phenotypes from that, again, using machine learning tools. And then you go to the literature, so people have fought a valiant battle, and all full-text publications are pretty much open to our software tools right now. So again, use machine learning to crawl the entire body of literature out there and extract all known monogenic diseases, all known monogenic variants, and all known diseases, all known phenotype sets that they are known to cause. And when you do that, all you have to do is score from variants. So you go from every single patient variant to every single paper relevant to them, to every single set of phenotypes presented in the papers, back to the patient set of phenotypes. And it turns out if you score all of these, the patient diagnosis comes at the top. We know how to attach scoring functions that would get your patient diagnosis to the top, making it an easy process for the computer. Okay, so solved phase one. Let's do phase two. Okay, and maybe before we go there, let's do some hand-holding. We do not replace the expert, right? We augment the expert. The expert calls the phenotypes. The experts approve every single diagnosis, right? And we do learn, obviously, from some of the harder cases. And finally, the system relies on our expertise of calling novel diseases and on referring the papers that call these novel diseases. Okay, so phase one is done. Let's do phase two. In phase two, we have to discover all remaining monogenic diseases. Turns out that is pretty easy as well. Let's do that together, okay? You look through all of your undiagnosed patients, and what you're looking for, first of all, you take all of their medical records and you extract patient phenotypes from them. And what you look for is, and then you compare all patients to each other. Again, notice these are operations that would take us humans a lot of time to do. They're impractical for us, but they're exactly the operations that a computer will do for you. Compare all patients to each other, find a small group of unrelated individuals that seem to have the same set of phenotypes, sequence them, and you have the causal gene. We've done that over and over and over again. You can go with groups of people as small as 3. Find 3 unrelated individuals with a similar set of phenotypes, sequence their genome, compare that to all the hundreds of thousands, maybe coming up to 1 million healthy individuals that we have sequenced, and the causal gene will come to the forefront every single time. Okay? Okie dokie. So, done, right? But then you say, hold on. For this one, I need 3 people, right? For a rare disease, maybe there are 3 of them in the world, maybe there are 3 of them in the US. What if I have one here at Stanford, one in Minnesota, and one in Arizona? We have hospital silos, right? Via HIPAA rules, et cetera. Hospitals are not allowed to share this information. So what do? How do we come up with these 3 individuals? Well, this is what was mentioned at the introduction. We've developed these that's interesting, I think. These cryptogenomic ways, okay, not well, they're cryptographic as well. This is what we call cryptogenomics. We developed this cryptogenomic way or cryptographic tools to allow us to do these computations, right? We compare all patients' phenotypes to each other across hospital silos. We can even sequence patients and discover their joint causal gene across hospital silos with 0 information leakage. So we respect the law to the letter, and we allow different hospitals to compute the answer together without ever sharing their inputs. So now we're really done, right? We have the second phase. We can hook up, connect these different hospital systems to find these small groups of people, sequence them again at their different hospitals, get the causal gene every single time. Okay, so done with 2. Number 3, we have to repeat this in a cost-effective manner. So let's look at this again. What was patient diagnosis for us? Find 1 or 2 variants that, according to the current literature, best explain the patient's set of phenotypes. Okay? We've automated the extraction of all of these modalities. Okay? So for all undiagnosed patients, if you have this thing automated, you can have it pulsate every periodicity you like, every year, which is what is done manually right now, every 6 months, every day. It's automated, it's computerized. So for every patient, in whatever periodicity you choose, you can ask, is there anything new to them? Any new genomic sequence? Maybe I have an improved variant calling algorithm. I can see more variants in the same data now. Maybe I have a new omic modality that I've just made for this person. Any new paper published for any of my undiagnosed patients yesterday, okay? Any new phenotypes that shows up in the medical record. Maybe many of our patients are children, very young children, and as they grow up, more phenotypes get added. Intellectual disability is revealed later. Many, many phenotypes unfold as the patient matures. So we have now automated access to all of these. So if any of these are true, you can ask yourself, hey, do I now have a diagnosis that is better than all the previous, I have a hypothesis of a diagnosis that is better than all the ones I've given before. And if I have one, it's a good one to show the expert. Okay, so like I said, you can repeat this periodically. We actually went out and did the toughest of these 3, I think, which is we went to the literature, and we have a system now that's up and running that wakes up every single morning, reads, I forget how many tens of thousands of papers that were published in PubMed yesterday, goes and gets the full text of all of them that appear to be monogenic, extracts everything that we need from them, and compare every single paper to every single undiagnosed patient we have. It's running. Proof of principle has been done. And in this proof of principle example, which I'm sure we can improve on, if you're willing to read 1 paper per patient per year, will get you almost all diagnoses as they come out. Okay? All right, done. So what's left? What is left? What is left seems to me is, we have to incentivize our society to actually do this, right? Healthcare is an industry. Its practice is an industry. It's a big, profitable industry. How do you make it change? That's beyond me. Lobbying, legislation. I talk to some of my friends and tell me, how much does an exome cost? I tell them, $250. Okay, $250, you get an exome, you can get a diagnosis, a definitive diagnosis for a person. Say, $250, if I give you a pilot for 10,000 people, that's $2.5 million. We don't need pilots. We're done with the pilots. The pilots look great. Pilots are done. What I think we need to be thinking is, if any of my patients runs a tab of 2,500, 2,500 I think here in the US is less than a day at the hospital. You can go up to 25,000 if you like. When they start running their tab, it's time to sequence. Currently, for any 2 individuals we sequence, one of them gets a diagnosis. If you find your 3-person cohorts, almost every single one of them gets a novel disease diagnosis, which you can go back and diagnose all the other patients waiting for that. And finally, we've shown that in the out years, all of your undiagnosed people, 10% of them get sequenced again and again in the out years. So everybody trickles out. Every disease gets a name. Every patient gets tagged with their disease, matched with their support group, and then shepherded to the next station, which is starting to think about a cure. But you have to have a name on the disease to start thinking about the cure. That's not done. That's a do. And I'll end where I started. Diagnose all of your monogenic patients. Seems to me that all you need is incentive. Thank you.
So this was fabulous. I think it's a great glimpse of how we can use technology to be able to really solve pressing healthcare problems. And I wanted to first start with a question to you, Greg, and I'll bring up this word of scale. Right? We think about it a lot in machine learning research, especially when we see new language models coming out almost every day. And I try to come up with analogies with medical imaging as a start. I think with large language models and large self-supervised vision models, there's a lot of data out there that's more or less homogeneous. But maybe with medical imaging, there's a lot of heterogeneous data out there. Do you think some of these typical self-supervised approaches that have worked broadly would work in medical imaging? And if not, how do you maybe see a path forward?
Yeah, so I do believe that self-supervised and unsupervised signals will work well in medical imaging. Because I actually believe that the space and manifold of medical images is smaller than the one of natural images. They look unusual to us because it's not what our visual systems evolved to process. But it's not. I don't think it's fundamentally a bigger space. But what you need to I think what we need to understand is that if you do self-supervised or unsupervised learning on an underrepresentative data set, you may come to understand that space in a way that's fundamentally incomplete. So I think that what we need larger, more open, more diverse data sets. But they're not mind-bendingly large. I actually believe that they're very much within reach. We have the data as a global community. We just need to find ways of being able to learn from them in aggregate, possibly through cryptographic means, learn from them in aggregate to understand what kind of representation we want to work within. And the more we're able to standardize representations and update them periodically as new data come in, I think the better off we'll be.
And then maybe since we're on the topic of representations, Gill, I wanted to ask you this question. In your 4-step approach, you described how we can come up with this nice embedding space for the EMR to really figure out which patients we want to be able to target. I'd be curious to get your take on how you think about this representation space. Is it a representation space across all EHRs in the world? Or do you think that because healthcare systems are fragmented, EHRs can be different, even within the same system? There could be non-stationary movement. So how does one maybe contend with some of these challenges where there's fundamental distribution shifts within this embedding space, but we still want to be able to look at it broadly?
Yeah, absolutely. I would say on more than one level, we are all humans. So if we're all humans, and most of the diseases I showed you are penetrant diseases, which means that no matter your ethnicity, no matter your gender, no matter how much lettuce you eat, if you are unfortunate enough to have some of these variants, you would have the disease. So I would think that despite the stationarity issue and despite cultural differences, language differences, we're ultimately all humans. So from the patients, they come to us in all shapes. I think we can transform the EHR to capture that essence and match all of them to each other. All.
Thank you. And we have a speaker question, so please feel free to introduce yourself briefly and then ask your question.
So, hi, my name is Mark. I'm from the Duke Institute for Health Innovation. So I have a question for Greg, and I'll kind of share two experiences to frame the question. So it's about kind of the complexity of trajectory modeling and helping drive behavior change, which I think ultimately, or treatment or interventions, whatever you want to think about how we actually affect outcomes. So one is 5-6 years ago, we worked on a chronic disease project, and we had a much more advanced trajectory model that we had built for clinicians. And clinicians ultimately wanted to reduce that to a point estimate of achieving some outcome within a certain amount of time, and then what to do with that. So I think there's one limitation, even when you're working with an expert clinical audience, of how much complexity is seen to be valuable for that person. And then the other experience, which was much more jarring that we're still all living through, is COVID. And so the first year of COVID, I worked very intensely on the COVID response. And I think just in terms of general public, the inability to think probabilistically about, does a mask work? Does a mask not work? What does a positive rapid test mean? What does a negative rapid test mean? And just like complete kind of failure of scientific communication to be able to build that competency. So I think these are really neat ideas. I'm just curious, like what's the work that we have to do in parallel to actually be able to execute them?
Yeah, it's a great question, and I think these are very real challenges. But sometimes with a problem like that, I think that we can solve it by stepping back and looking at what the real drivers and incentives are. So when someone comes in and they get diagnosed, they want to know what's going to happen to them, right? That's kind of one of their first questions. What's going to happen? And I believe that this kind of trajectory modeling, which, to be clear, I'm not necessarily saying that we have to, formulate some differential equations that drive things in the space. I actually think these are the kind of things that can be arrived at empirically if we just if we imaged normal patients and diseased patients enough times, we would build systems that implicitly understood the trajectories. I think that there's so much value in being able to say to the individual, not in this abstract and actually quite inaccurate way that we currently do prognosis, but to actually be able to say, well, this is what we expect for you. And I think that adds so much value to be able to answer that kind of question that eventually things will move, but we're in this uncomfortable intermediate state where there is a drive to want to oversimplify, right, and project something down onto a unidimensional quantity or something that just captures, well, what is the disease state? So for example, like and I think sometimes that has really negative clinical impacts. So for example, I think like in Gleason grading for prostate biopsies, right? We've established a relatively low dimensional scoring, and I think that we're throwing away a lot of information by doing that, and that is actually leading to less accurate prognosis and less actionable treatment recommendations. And I think if we get a few of these demonstrations of where you saved lives or you improved the quality of life for your patient by not reducing too soon, I hope that will drive change, but...
Yeah, my follow-up is, how do we test the assumption that it adds value to decision-making? Because I think we have some cases now where we have good trajectory models, and I would just be curious, like what you see as the first steps of really demonstrating that.
Yeah, I think it's going to depend on the actual use case. I imagine that there are going to be diseases where doing the trajectory modeling is tractable, but it's not very inspiring. It's not very actionable. It doesn't change what happens. But I believe that science and medicine and industry, they are fundamentally human endeavors, and there's sociology and excitement in all of them. And I think a small number of powerful and exciting examples can change the way that people think about them. But it's up to all of us to stumble upon those. I don't know that we can set out a research program to say, this is how we find the right ones. But I believe that they're out there, and I'm frankly inspired that there are people that are already thinking about how we model the trajectory and come to understand how we might intervene. But I agree that fundamentally, until you have real people who are being saved and being helped by this extra set of work, it'll continue to fall flat.
Yeah. And along similar lines, I have a question for Gill. Really trying to think about taking this conversation further and really trying to get some tangible clinical impact. And as technology creators, how does one think about the role of regulatory bodies in this place? If we want to be able to err on the side of doing, but at the same time we want to be doing this in a responsible manner, in a way that's compliant from a regulatory standpoint. How do you think about that? And maybe I'll let Gill go first, but I'd love to get your take on that too, Greg.
Yeah, absolutely. I think the response should be two parts. First part is we as technologists have to understand what legislation and what rules of society we have to abide by. And whenever we can, with whichever tools we can, we should simply do it. But also, whenever there is a place where we think that expanding those boundaries a bit could be of great help to certain populations, we could maybe try to push them out. But certainly first, for example, the cryptographic examples I showed you were really motivated by going with the letter of the law. If you want us to, if we are able to compute outputs together without ever sharing inputs, that's exactly the letter of the law right there. We can respect it, we can abide by it, and we can give extra benefit to our patients. So the combination of these two things, I think, would be key.
Great thoughts?
Yeah, I completely agree that and I do, when you stand back and you look at the mission of these regulators, right? It's to know that treatments are safe and effective. It's our job to help show how you know that a machine learning system is safe and effective, right? When anti-lock car brakes came out, right, we had to show that something that periodically turned your brakes off while you were trying to drive in an emergency situation was both safe and it was effective. You actually stopped in a shorter distance. I think we need to take that same kind of approach to working with regulators so that they understand, because it's fundamentally different to try to understand whether a machine learning system is safe and effective, particularly one that we want to be learning in an online fashion from every new patient. To have a learning healthcare system, how do you have a learning healthcare system that's safe and effective? That's so different from knowing whether a single small molecule is safe and effective. I believe that it's tractable, and until we can come together and find ways that we all believe in of identifying how an algorithmic approach is safe and effective, I think we're going to be at a loss, because we need it. There will be algorithmic implementations that are out there that are promising on a small subset of data, but they either are ineffective or they are dangerous. And so we need to be able to understand how to measure these things so that we can help regulators apply that same standard across the board.
Great insights. Thank you both. And maybe in the interest of time, maybe we'll finish off the session with one last question. Please go ahead.
Thanks. Thank you for the amazing talks. So I'm Mel, and I'm a postdoc in Dr. Joyce Delsa's lab in ophthalmology in Stanford. And my question kind of is directed at Greg, but I'd love to get both speakers' opinion on this. So first, it's kind of stemming from a rather specific interest. So I do image analysis on OCT images, and right now we're just doing segmentation, but we're hoping with segmentation it will eventually lead to sort of being able to diagnose. A really fundamental problem with it is that basically a lot of OCT imaging, if there's any ophthalmologists in the audience, is rather gatekept by kind of three massive companies. And the images that they produce kind of look similar-ish maybe to like our eyes, but deep neural nets are incredibly sensitive to textures. So I feel like because of that, there's a lot of like little pockets of efforts being made by labs across the world, but it's not really kind of, there's no synergy between them. Like one machine that's made by this pocket of data cannot be used to predict something else. So kind of wondering on like your opinion of a solution for that, or like what you think could be a solution for that, which, sorry, also leads on to a second question, which is like this kind of idea of how can we band together all these like little efforts? Because it seems like if you go to a conference, so many labs are trying to do the exact same thing and they do it very well, just like what you just mentioned, which is like they do really well on small pockets of data and they come up with an F1 score and it looks amazing, but then what? Like now what do we do with that? So just wanting to get your opinion.
Yeah, so siloed data is hurting us in a lot of ways, right? And it is true that the same way that I said the machines can see things that we can't see, that's good and bad, right? They can also anchor on noise or be completely thrown off by a different set of distribution and how the image is taken. And this is something that we've dealt with a bunch of times in my group at Google, where you sometimes, if you work with one imaging device and you try to transfer that model to another device, you take sometimes a substantial decrement in quality. And there are solutions if you have some amount of data from all of the imaging devices that you want to work with. You can learn, often in a semi-supervised way, to build systems that work well on all devices. But if you only have access to one device, then you just don't know how bad it might be when you make the move. And so fundamentally, I think that the view here has to be one of making data available in a way that we can build systems that operate in the totality of what's available, and that when a new device comes out, we can rapidly learn to be able to operate on it. And I think this comes back to Gill's point around incentives, which is that right now, there are incentives for these things to be somewhat siloed and for things to be proprietary. That may be good for one company's bottom line, but it's actually bad economically in aggregate. We are wasting money, right? There's more value to society in being able to find ways to bring those things together. And this may be, I also don't lobby or legislate, but it may be that some notion of having data availability with appropriate controls on privacy, maybe that's something that we need if we're going to solve this problem. Because otherwise, you make this great point estimate where you're standing, but then you go and you project it out into real data and you don't know what it's going to be like. And that's something that we've seen when we take our algorithms into the real world. And why I think post-market monitoring is going to be so important is that when you get out there in the real world, the distribution is richer than you thought it was. And that's good for version 2 and the patients that are served by version 2, but you better be on it in version 1, otherwise you're going to make mistakes.
Gill, any parting thoughts on this topic?
No, I think Ray covered it beautifully. Couldn't agree more.
Wonderful. Well, I'd like to thank both you and Greg for this really insightful set of talks and this panel. I feel like we learned a lot. And I think there's a lot of open challenges as a community, but I think being able to better share data, to be able to share a lot of code that's reusable and reproducible, I feel like that can go a far way in trying to at least come up with initial solutions for some of these problems. So thank you again both for your time.
Thank you.
Thank you.
Yep.